Alright, so today we're going to be talking about lesson 6.2, which is base E and logarithms. So the natural base E, also known as Euler's number, is an irrational number, but is not a variable. So it's similar to pi. You know how pi is a number represented by a symbol, and it's irrational, meaning it doesn't terminate. The decimal points go on forever. And it's approximately 2.71828, and the decimals just keep going. So you treat it just like a number, and you'll see it on your calculator. If you hit the second ln button, you'll see e to the x. You'll see it on the little, like the non-button part of the calculator. You'll see an e. That's how you get it on the calculator, and the phone has it as well. I think in the same position. But if not, if you're stuck and can't find it, at the end of this lesson, I can come around and help you find it on your calculator and all of that. So, the natural base exponential function. This function appears in nature and is used to describe continuous growth and decay. So, we use this base, and we put it to powers of different things to calculate continuous growth, because it has this exponential model that models things in nature, and we use it for finances as well. So we're going to learn to evaluate E. Just start it out simple. Just talk about how we put E to a power. So the procedure used to do this will depend on what kind of calculator you have. Every calculator is going to be a little bit different. So you do need to kind of figure out how to do it on the calculator you're going to be using. So I'll just talk about it in terms of this standard calculator that you use in geometry. Okay. What you have to do to type that in, if any of you have that calculator, is you type in the exponent first. So you type in 4, and then you hit second ln, and that's putting e to the 4th power. And when you do that, we're going to round to the thousands place. You get 54.598. So remember, E is a number that is approximately 2.78. So you're just taking 2.78 roughly and putting it to the power of 4. Now remember, everything that you calculate with E is an approximation. And why is it an approximation? Why is it not exact? Good, E is an irrational number. If you take a rational number and put it to a rational exponent, it's still going to be an irrational number. So everything you calculate with E is going to be you're going to have to round it. So let's try the next one. This is just a calculator operation. So to do this one in my calculator, I type in 2 negative, make it negative, and then second ln. And when you do that math, you should get approximately 0.135. Alright, and on this one we're going to take the square root of E cubed. Now there's two ways to do this. The square root of E cubed is the same thing as E to the 3/2 power, so you can calculate this either way. I'm going to show you the first way. So what you would do is you would do E to the 3rd power, so 3 second E, and then you'd hit the square root button. And when you do that, all these answers are approximate. I keep just forgetting to use the approximate equal sign, but they are approximate. And that's going to be 4.482. And if you do it this way, you'll get the same answer. So 2 divided by 3, second E, and you'll get the same answer on that. So that is how you do the calculation. So does anybody have any questions about what we're doing so far? Alright, so we have one more to try. So this is E to the 2/3 power. So we're going to do our approximate calculation. So the easiest way to do this is to type in 2 divided by 3, which is going to give you 0.6 repeating, and then second E. And when you do that, you should get approximately 1.948. So the reason we wanted to practice these is because we're going to be using E in formulas, so you need to know how to put E to a power in order to utilize these formulas. This is just pre-practice, okay? So any questions before we move on to the next slide? Okay. So now we're going to move on to talking about compound interest. So for everybody who says, when am I going to use this in real life? Okay, this is your time to shine right now. All right, so we're going to be talking about all the taxes stuff and all the financial stuff that you guys always ask about. So let's talk about the concept of compound interest. So before we get into compound interest, let's go through some terminology of what we use, what these variables represent. So A of t is the amount of money after time t, okay? This is like the end result of your answer typically. Now P, the letter P, is known as your principal. So have you ever heard about loans? You might hear this on commercials, and they talk about the principal amount. This is the amount that you start with in an account. If you're going to be investing, what the money that you invest is called the principal, okay? And R is known as your rate, also known as your annual percentage rate, your APR. You guys have heard of APR in finance, where they talk about the APR of a credit card and whatnot. T is time in years. So I want to just mention the year part. This is a little bit ambiguous. It doesn't have to always be in years. But what this really means is time has many units, right? Can you think of another unit of time other than years? Minutes, seconds, hours. There's so many different units of time. Now the main thing we need to make sure of here is if we are using time in a different unit, we need to be consistent throughout the whole problem, okay? So if the setup of the equation deals with months, we need to plug in months. So whatever your setup is, it needs to match what you're plugging in. You can't swap around units. And you probably learned this in chemistry and physics as well. Units have to match, okay? Now n is the number of yearly compounding periods. So how many times a year it's compounded. Now the way they can give you this information is they could just straight up say it's compounded 6 times a year, it's compounded 5 times a year. That's one way it can be put. Or they use these vocab terms. So we put out a few of them here for you. They'll use the word annually, semi-annually, quarterly, monthly, weekly, and daily, okay? So what each of these mean is they mean a different amount for n. So annually means 1, semi-annually means 2, quarterly means 4, monthly is 12, weekly is 52, and daily is 365. So your n value is based on either them telling you one of these words that you use or them just directly telling you the n. And there are 2 formulas that we use for calculating compound interest. And these 2 formulas are used for different things. So the first formula is what we use when we compound over a certain period, okay? This is the formula you use when you have an n value, a compound value. And if you have what's called compounding continuously, you'll see the word continuously in the question, which will be a good indicator of that you need to use that formula. This is the formula we use, and you'll notice that it doesn't have n in it. But instead of n, it has what? E. And the reason we use E is because it shows continuous compounding, natural compounding. We use the base E. So E is actually a number, remember, about 2.78, and that's what you're going to use in that formula. So let's put this into practice and try using one of these formulas. So let me zoom out for a second because I think this slide is a little cut off. Let me just adjust that. It's been bothering me. There we go. That's better. Okay, so the first question says, you invest $10,000 into a certificate of deposit. This is called a CD. It's a type of account that offers 3.9 annual percentage rate, APR, compounded quarterly. It matures in 5 years. How much will the CD be worth at maturity? So basically, you invest $10,000 at a certain, they're telling you you're going to gain a certain percentage of money based on this investment, And it takes 5 years to mature, so your money's locked away for 5 years until you can take it out, and it's going to be a higher amount at that point. So first thing we need to do is identify each variable. So what is your p-value? What is your principal? The amount of money you start with. $10,000. Good. You start with $10,000 initially, right? Good. So you start with $10,000. And what is your APR, your rate, as a decimal? Remember, you have to convert it to a decimal if it's a fraction. If it's a percent. So what would 3.9% be as a decimal? 0.39. Not 0.39, but 0.039. Because you have to move the decimal place 2 times, remember? To the left. So just make sure, that's a really big difference, because 39% interest is a lot bigger than 3.9, so just be careful with the number of times you move the decimal place. And, bless you. Now we're looking at n, which is the number of times it's compounded. Now they didn't give us a direct answer on this, but they told us it's compounded quarterly, which means your n is what? 4, according to your little table. And then lastly, time in years. How long is it going to be maturing for? 5 years. So we have 4 pieces of information. And which formula are we going to use here? The first one or the second?
First.
Good. The first formula. How do we know we're using the first formula? Because we have a what? Not because we have time, but because we have... The other one has time. What's the other one missing?
The exact amount of years.
It's missing the compounded. How many times it's compounded? The other one's compounded continuously, so it doesn't have an end. So using this formula, we're going to plug everything in. So the amount of money after 5 years, A of 5, is equal to your p-value times 1 plus your rate divided by n to the power of n times t. So this is all the work of your calculator, but remember, order of operations is still a thing you have to worry about, especially on these scientific calculators. It doesn't do order of operations for you exactly. So parentheses or grouping comes first, and inside the grouping we have addition or division. We know division comes first, so we do, in your calculator you would do 0.039 divided by 4 plus 1, and I've just calculated what's inside the parentheses. Then I'm going to put it to the power of what? 20. And then I'm going to take that amount and multiply it by 10,000. And when I do all of that math, my answer is 12,141 and 64 cents. So basically you had $10,000 to invest, and you had the ability to you have to use that money for 5 years. So in doing that, you were able to gain, $2,000 something on that money. So that's kind of how investment works. You have to have enough money ahead that you don't have to use it for 5 years. Most people don't necessarily have $10,000 to set aside that they can't use for 5 years, which is why it's not always this simple, in reality. But that's the general idea. All right, so let's go ahead and try 3. Does anybody have any questions about example 2? All right, let's go ahead and try 3. When you were born, $10,000 was deposited into your college fund, paying 5% APR compounded continuously. 18 years later, you head off to college. How much money is in your college fund when you arrive on campus? So let's see what we know. What is the p-value? What is the principal amount? Good. You start with $10,000. And what is your rate, your APR?
0.05.
Good, 0.05. Very good. And what is your the amount of time? 18 years. Now, is this one compounded at a certain rate? No, it's compounded what? Continuously. So when it's compounded continuously, which formula are we going to use? The second formula, good. So that's A of t is equal to your principal amount times e to the power of r times t. Remember, e is a number. Okay, it's not a variable. So you have only one variable you're solving for, which is a. So a of 18, basically the amount of money after 18 years, that's what this notation means, is equal to, how you would do this in the calculator? The easiest way to do it is you do 0.05 times 18 equals, and then second e, and then times 10,000.
Can you say that one more time?
How to do it in the calculator?
Yeah.
What kind of calculator you have?
I'm using the phone, but it's working.
Is it? On
Yeah.
that, not the sideways one?
Yeah, no, it's working. Like,
Oh, I got you. Okay, yeah, so you have to put e to the power of 0.05 times 18, which is 0.9, and then times 10,000.
Okay.
Did that work for you?
Yeah,
If you guys are having any calculator issues and you need like one-on-one help, I can come around after and like help you out with any of your calculator troubles. Just because I know everybody has a different one, it's kind of hard for me to like give one direction, you know?
yeah, it worked.
It worked? Okay. Perfect. I think I added an extra 0 in there that shouldn't be there. Yeah, I was going to say, that's a lot of money. Yeah, hang on. There we go. That's what it is. I put a 0 twice instead of once. So, basically, you end up with $24,596.30. So, if you have enough money to put away $10,000 for 18 years, you can over double it. So does anybody have any questions about this one? About rate interest and all that? Does that make sense? All right. So, if that's good, we're going to move on to something more sciencey. We are going to move on to half-life. So, you guys have presumably probably taken chemistry, or you are in chemistry right now, or you could be in physics. You use half-life in physics, but not as much as probably in chemistry. So you probably have talked about half-life in chemistry, right? A little bit? Not yet. You're probably not there yet if you haven't taken it, or if you're in it. So what is half-life? Half-life is the amount of time required for some substance, so radioactive, biological, or chemical, to be reduced, decayed to half of its original amount, its half-life. So basically what this means is each chemical has a different half-life. So one chemical might have a half-life of 300 years, so it's not going to depreciate that quickly. But some chemicals actually have a really short half-life, a few hours, so they don't last very long if you have a sample. So you have to keep that in mind in storage and all of that when you deal with these chemicals, or these elements and whatnot. So the formula for half-life is A of t is equal to A sub 0 is equal to 1/2 to the t minus k, or t over k power. Now for some reason, I realized this on your print, your example 4 and 5 are the same for some reason. So you guys will just have to copy down 5 after. But we'll just do 4 first and then we'll talk about that. I don't know why that happened. Alright, so example 4. The radioactive element, or a radioactive element, not the radioactive element, has a half-life of 250 years, and there is currently 42 grams of the element. How many grams of the element will remain after 462 years? So the first thing you want to do is identify the original amount, A sub 0, which is basically the same thing as the principal in the last problem. So how much of this amount of the substance did you start with? 42 grams, good. How long are we allowing this substance to decay? Good, 462 years. Good. And what is its half-life?
212 years.
Good, 250 years. So both time and T and K are both going to be in units of time. Make sure they're in the same units of time. Very important. Are these using the same units of time? Yeah, so we're good to go. So the formula is A of T, so A of 462. So the amount of the substance left after 462 years will be the initial amount times 1/2 to the power of T divided by K. So if you're doing this one in a calculator, you're going to have to use the parentheses because you're going to have to put 0.5 to the power of 462 divided by 250. So 0.5 to the power of, parenthesis, 462 divided by 250, end parenthesis, equals, and then times 42. Which, when I do the math, my answer is approximately, I keep forgetting to put my approximate equal signs, 12.67 grams. So what this means is, after 462 years, there will only be 11.67 grams of the substance left. So far, does this question make sense? Do these questions make sense to everybody? Okay. So we're just using real life applications and whatnot. Alright, so I'm going to give you a minute to write down example 5, because I guess you guys have example 4 twice. Alright, so potassium 42 has a half-life of 12.4 hours. So how much of 1,000 grams will remain after 3 days? So what's the initial amount that I'm starting with, A sub 0? How much of the substance do I start with?
1,000.
Good, 1,000 grams. And what is my half-life?
12.4.
Good, 12.4 hours. And what is my amount of time that we're measuring it over? 3 days. Now here's like a red flag right here. Hours and days, are those in the same units? No. So you either have to convert both of them to day units or both of them to hours. I prefer to always go to the lower one because that way you don't have to deal with as many decimals. So I'm going to convert them both to hours. You just have to make sure they're matching. So how many hours would be in 3 days? Good, 72. So 72 hours is your time. So those are the 3 pieces of information you're going to need to set up your equation. It's going to be A of 72. So the amount of potassium 42 left after 72 hours will be equal to 1,000 times 1/2 or 0.5 to the power of 72 divided by 12.4. And when we do that calculation in the calculator, remember, due to order of operations, if you put 1/2 to the power of 72 divided by 12.4, it's going to calculate the power before the division, so you have to put in parentheses to counteract that. So 0.5 to the power of y to the x, parenthesis, 72 divided by 12.4, parenthesis, equals, times 1,000. So the amount of the substance that will be left will be approximately 17.87 grams. So if I zoom out here for a second and we compare these two substances. So this substance only decayed for 3 days, and we started with 1,000 grams. And this substance we only started with 42 grams, and it decayed for 462 years. And see how we still have only just marginally more of this substance? So this substance half-life is much quicker. Okay, it decays much faster than the first one. So any questions about that? Alright, so now we're going to move into the next portion of the notes, which is on the back, defining a logarithm. We're going to do the first part of this section, and then we will break for lunch and come back to it. So let's look at the definition of a logarithm. Okay? So a logarithm is basically a tool to help you find an exponent. Okay? We use it in math to help us find an exponent. So for example, this is the setup, and use the button on the calculator to calculate it at times. This is the base of your logarithm. This is the answer, and this is the power. And how this looks in terms of a regular setup would be x equals b to the y power. So here's an example I want to show you really quick so you can kind of understand why a logarithm would be useful to you. Okay, this is just like a side note. So, say I said 2 to some power x is equal to 16. Now, just using your brain, you could probably figure out what x is, right? What do you think? 4. So you were able to find out that the answer was 4 because this one was very simple, right? But what if I gave you something more complicated? Like I said, 1.5 to the power of x is equal to 45.8. You can't just figure it out in your head what x is, right? We have to have a tool to solve for x. This is what the logarithm does. Okay, the logarithm allows us to find this x value using algebra. So logarithms solve for missing exponents. That's just something in math that we don't have another tool for. You haven't learned about the tool for that yet, and that's what this is. So I just want to put in perspective what a logarithm is used for. We're not going to be doing too much with it today in terms of like solving. We're going to do more of that next lesson, but I just wanted to kind of give you an idea of what it is. Now logarithms deal with exponents, so they do have restrictions, okay? There's 3 types of restrictions. Your base has to be greater than 0, your base cannot be 1, and your x has to be greater than 0. Now, does anybody know, looking at this, why would the x have to be greater than 0? Any ideas? Yeah.
Because if the x is 0, then like you can actually have an answer.
Exactly. Yeah, so we know that some number put to the exponent of some number can never be 0, right? There's no x number that you can put to a power of something that will ever give you 0. So that's the reason that we can't have your answer be 0. It just won't ever happen. You'll get an error in the calculator if you try it. And your base can't be 1 because your base, basically if you put 1 to any power, what is it always? 1. So it's never going to come out to be something different. That's why we restrict it in that way. So yeah, just a few things. So when you encounter a logarithm, rewrite the expression or equation by thinking the answer is the base raised to the power. So something important that we do with logarithms is we have to rewrite them in terms of the exponent. They have to be rewritten both ways. So this is the interpretation, how it's written both ways. So I'll zoom in here and talk about this for a second. So this is the setup. Now the way that I always learned it was, if I want to go from log to exponential expression, or exponential equation, my math teacher always taught me to use the arrow method. So 2 to the power of 3 is equal to 8. So 2 to the power of 3 is equal to 8. That's its expression written in terms of exponent versus log. So every exponential expression or equation and expression that you write can be written in terms of logarithms as well. So today we're going to focus mostly on notation because notation alone in this topic takes a little bit of time to learn, and then we'll do more application. We'll just do basic application today. So let's do a few of these together, and then we'll take a break until lunch. So it says use the definition of a logarithm to rewrite each logarithmic expression or equation into an exponential form. So you have to be able to go from exponential to logarithm and vice versa. We're going to practice both. So the way you do that is 3 to the power of 2 is equal to 9. That's how the notation works. Okay. So using that logic, what is the b going to be? Good. 6 to the power of 3 is equal to 216, or 216 is equal to 6 power of 3. Yep. So any questions on these so far? Alright, so the next one is going to be 4 to the power of negative 2 is equal to 1/16, which is true. And the last one would be 9 to the power of 3/2 is equal to what? 27. So that is how you go from logarithm to exponential. Now, we will go over the next set of A through D when we come back, but what I want you to try is, now that we see how to go one way, can you figure out how to go the other way? Can you write the logarithm by using, your logic to figure it out? See if you can figure out the other way. And then we'll go over those when you come back, and then we'll continue with our notes.